first, let's look at the interface of graphs. So the interface of a graph looks like this. Clearly it consists of vertices and edges, as you already know. And here are all the methods that a graph must implement. I think they're all pretty straightforward. So you can pause the video if you want to have a look at them. And if anything is unclear, then you can check what it means in the book. So there's a number of ways to implement graphs. I'm going to be showing you 4 of them. And the first one is the edge list structure. So you can see the code to implement it here on the left. And you can see an overview of how that looks like in a computer on the bottom right. So if we, for example, implement the edge list structure and we have this as an example graph, the data stored in the computer would be like this. So you see the computer stores a set of vertices and a collection of edges. And each edge points to the 2 vertices that edge connects. So to be able to understand this a little bit better, let's look at an example. So say we want in this graph to check whether U and W are adjacent. What we would need to do is check for each edge whether it connects U and W. And as a matter of fact, if we go to G, we see it connects U with W. Going through the vertices wouldn't work, because if you go to U, there's no additional data stored in U, so we wouldn't know if it's connected to W. So we need to go through all the edges in this implementation. Then we have the adjacency list structure. So this is implemented, again, the code's on the left, the overview on the bottom right. So this is implemented as a set of vertices, and each vertex stores the edges incident on that vertex. So in this graph, U stores E and G because E and G are the incident edges on vertex U. So if we here want to check whether U and W are connected, we would simply go through to U and W and check whether the edges of U and W, if there's an edge that is in both of them. And as a matter of fact, there is, because G is in both U and W. So we know U and W are adjacent. Then there's the adjacency map structure. And this again stores the vertices as a set. And in each vertex there is stored a map which maps the adjacent vertices to the edge which connects U with W. So here again, if you want to check whether U and W are adjacent, we go to U and then we check whether W is in the map. And we can see it is, and it maps to G, so G connects U and W. And in W we could have seen the same thing. And the final implementation is the adjacency matrix structure. So here the graph is structured as a matrix where there's a row for each of the vertices and a column for each of the vertices. And in each cell is stored the edge that's between the vertex of the row and the vertex of the column. Unless they're not adjacent, then nothing is stored in the cell. So again, if you want to check whether U and W are adjacent, you would simply go to the row of U and the column of W and check whether there's an edge there. And in fact there is, namely G. So this matrix, of course, is a 2D fixed size array. Okay, so these are the 4 implementations I want to show you for this video.